Uno, dos, probando, probando, uno, dos, tres, uno, dos, tres, sí, uno, dos, probando, probando, uno, dos, tres, uno. Uno, dos, uno, dos, 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 sí. Uno, dos, uno, dos, uno, dos. Uno, dos, uno, dos, uno, dos, uno, dos, 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 dos. Uno, dos, uno, dos, uno, dos, uno, dos. Uno, dos, uno, dos, uno, dos. Dos, 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 dos. Sí, sí, uno, dos. Uno, dos, uno, dos, uno, dos, uno, dos, uno, dos. Uno, dos, uno, dos, uno, dos. Uno, uno, uno. Dos, 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 dos. Uno, uno, dos, uno, dos. Uno, uno, dos, uno, dos, uno, dos.
can, do you have this one when you need me?
Okay, okay, sure.
And switch.
Do you want
Good morning, everyone. How's everyone today? Good? Awesome. So welcome back to the day 3 of our workshop. Hope you have been up to the speed of the techniques that has been taught during last 2 days. So we are now basically going to another level in terms of the modeling, which my colleague is going to basically lead the training on bottom-up population, the concept, and specifically working on Bayesian statistical framework. So hope you have a good day, a good training session, and please always let us know if something is not clear or you have a question or concern, or you want us to basically repeat just for you to be able to understand before we basically move into another topic. So thanks very much again, and hope you have a great day. Please.
Hola. Yeah. Good morning, everyone. So today we are actually going to do the actual population modeling that you guys really want to learn. All the things that we've been doing so far is just to give you some foundations, so that we progress as we go along. So today is actual population modeling. But before we zoom into the actual population modeling, we have to learn another statistics, because that is what we apply in our population modeling. So this is more of like another higher level, right? You don't really need to grasp everything, but see it as a foundation. We are learning something new to apply it in our population modeling, right? So the statistics we learned yesterday, and also when you go to college or you go to university, the statistics that they teach in schools is called frequency statistics. So what we did yesterday is frequency statistics. And the reason why it's called frequency statistics has to do with the fact that in terms of estimating probability, it's based on proportions or the frequency. There is another form of statistics, which is this one called Bayesian statistics. And Bayesian statistics sees probability as a distribution. And in actual fact, some of the decisions that you've taken in life is based on Bayesian statistics, just that you didn't think of it as Bayesian statistics. And I'm going to give you some examples to show you that that decision that you took was based on you using Bayesian statistics in real life, right? So just hang on from there. So before we delve into Bayesian statistics, we need to learn some terms, some definitions, which is relevant when we are talking about probability, because Bayesian statistics is all about probability. So this morning, we are going to look at basic probability theory. Then we will look at basis of Bayesian statistics and how to run STAN models in R using how to run Bayesian models using STAN, which we have all installed. Is there any person here who hasn't installed STAN? Okay, so we've all installed STAN on our machine. So we are going to use STAN today. And the objective of this introductory lecture is to understand some basic theory about probability. We also want to understand how Bayesian statistics works and able to implement it in a regression model. And the whole idea is that we want to be able to use it to predict population, which is the main focus of this particular workshop. Okay, so there are some key concepts and definitions that we need to get used to. One of them is outcome. An outcome is defined as a possible result from a trial or an experiment. So when you do an experiment or you do any trial, the result that you get is called the outcome, right? It's as simple as that. Then we have another one called event. And an event is one single outcome from a trial or an experiment. So when you do an experiment, one of the results that you get, only one value or one observation, is called an event in probability. The next term is mutually exclusive events. And we say that mutually exclusive events are two events that cannot occur at the same time. So when you have an event that cannot occur at the same time, it is referred to as mutually exclusive event. So an example of a mutually exclusive event is life and death. So the two events cannot occur at the same time. It's either you are alive or you die, right? You cannot be alive and dead at the same time, unless maybe you have some superpower to be alive and dead at the same time. So that is an example of a mutually exclusive event. Can anybody think about any mutually exclusive event? Something that you can think about. Things that don't occur at the same time. Any idea? Okay. Yes, so you can live or die, but is there any other one? I'm trying to think about another event. So when you flip a coin, right? When you toss a coin, you either have a head or a tail. Like the coin will land on its head or it will land on its tail. That's a mutually exclusive event because the coin will not stand, right? You have to get one option. That is a mutually exclusive event. Then we have what is called an independent event. And we say that two events are said to be independent if the occurrence of one does not affect the occurrence of the other. So when this event happens, it doesn't really affect the other event. So the two events are very separate from each other. That is an independent event. Then we have joint events. And we say if an event is joint, when the occurrence of one affects the other event. So two events are said to be joint if the occurrence of one affects the occurrence of the other. Those two events, they go along or they go together. So an example is you experiencing hunger and you not eating. So the probability that you go hungry has to do with the probability that you didn't eat, right? So experiencing hunger and not eating, they go together. I haven't seen any person that has eaten and then experiencing hunger before. Is there anyone like that? So the two events are joint events. They always go together. If you don't eat, you'll be hungry, right? Any other example? Any other example of events that always go together? Anybody? Two events that always happen together. Well, I'll give this. This is not like a perfect example, but we know winter always goes with being cold, right? So when winter happens, then you have the probability of feeling cold, right? So those two events goes together. It may not be a perfect example, but they always go together. So that is a joint event. Then we have another term called sample space. And sample space is a set of all possible outcomes of a trial. So the set of all possible outcome of a trial is the sample space. So when you flip a coin, the sample space is 2. You can only get a head or a tail, right? Coin has only 2 sides, either the head or the tail. Or when you roll a die, right? You guys know a die. It has 6 numbers, 1, 2, 3, until 6. So that becomes the sample space of a die. And we have the last one being sample point, which is one of the possible outcomes in a sample space. Okay. So what then is probability? Probability is the chance of an event occurring. So the likelihood of an event going to occur is what is known as probability. And this is a classical formula for probability. So in calculating probability, we have the number of outcomes that you desire divided by the sample space, or the total number of possible outcomes. And when you divide it, you get what is called, you get your probability. So if A and S denote the set of event space and sample space respectively, then if you want to find the probability of A, it's given by n into n, the number of A's divided by the sample space, and you get your probability. So for example, if we throw a coin and we want to find the probability of having a head, we have 1 head, but we have a sample space of 2, because you can either have a head or a tail. So when you divide 1 divided by 2, you get your probability, which is 0.5. It's as simple as that. So that is classical or frequentist way of calculating probability. Yes, so this slide here is showing the sample space when you toss a coin. It is either you have the head or the tail. So that is the sample space. So the probability of getting a tail is 1 divided by 2, which will give you your probability. Any questions so far? We are all on track, right? Okay. Yeah, here too we have a die. So when you roll a die, you have this sample space. A die has 6 sides. You get 1, 2, 3 until 6. So the sample space with the die is 6. So if you want to find the probability of, say, having a value of 1, it is 1 divided by 6.
Buenas, esa diapositiva no nos sale acá a nosotros, la de los dados.
Okay, yes, so yeah, I updated my slides today. So afterwards, I will give you this particular slide, right? So don't worry. Okay. Yeah, sometimes you prepare your slides and then you see some new thing and then you decide to add it to your slide, right? So yeah, I'll send you this new slide after we finish. I think it's only this one and another slide that I've modified. See? Okay. So here, what is the probability of finding an even number? By the way, what is an even number? Two, 4, 6, right? So assuming you have this sample space, right? What is the probability of finding an even number? How many even numbers do we have here? 3. So it's 3 divided by 6. And what will you get? 0.5, right? So 3 divided by 6, you get 0.5. Yeah. Yeah, okay. How about the probability of getting an odd number? What is an odd number? It's the same thing, right? So 1, 3, 5. So we have three odd numbers. We divide by the sample space, which is 6. We get our probability, which is also 0.5. So you see, probability is easy to calculate in classical statistics. Okay, this slide is showing that if you have 2 coins, right, and then you toss them all together, then the sample space you get is this particular set. So you can have a head and a head, tail and a tail, or you can have a head, tail, and you can have tail, head. So that becomes the sample space because we are tossing 2 coins all at the same time. Okay, so in probability, we have some axioms or some features of the probability that when you calculate, or characteristics of probability. And one of the axioms is that probability of an event is non-negative rare number that lies between 0 and 1. So when you calculate a probability, the value that you get should always be between 0 and 1. If you calculate a probability and you get negative value, it means you are wrong. You are doing something really wrong. And if you calculate your probability and you get more than 1, maybe you get 2, it means your calculation is wrong. You have to go back and see what you are doing all right. So probability is always between 0 and 1. Or if you want to convert it into percentage, it's always between 0 and 100%, right? So the probability that it will rain today can be 90% or can be 0.9. You can get a probability that it will rain today be maybe 2, right? That doesn't happen in probability theory. So that is one of the axioms or features of probability that that you need to be aware of. The second axiom is that the probability of the sample space is always 1, right? So when you take the sample space and you want to find the probability of that sample space, you always get 1. When you throw a die, when you toss a coin, the sample space is 2. So if you want to find the probability of that sample space, it's 2 divided by 2, and you get 1. So the probability of the sample space is always 1. And the third axiom is that if E1 and E2 are disjoint events, if 2 events are separate from each other, then the probability of their union is the probabilities of their individual event, right? So if 2 events are kind of independent, then the probability of them occurring together is a summation of their individual probabilities, right? So as we see in this slide, the probability of E1 and the probability of E2 is their individual probabilities, which is probability of E1 plus probability of E2, right? So these are the 3 basic axioms that we have regarding probability. Then we have another term called conditional probabilities, right? And conditional probabilities is usually used to evaluate joint events. So events that go hand in hand, like being hungry and also not eating. In terms of evaluating these 2 probabilities together, we use what is called conditional probabilities. And conditional probability, so if A and B are events and the probability of B is greater than 0, then the conditional probability of A given B is written as probability of A given, so this sign that you see here is given. The probability of A given B is a joint probability distribution between the 2 events. So it's, in terms of formula, the probability of A given B is the probability, the joint probability between A and B divided by the probability of B. That is called conditional probabilities, right? So I think the next slide, yes. This slide kind of explains it very well. The guy you are seeing in the slide is called Thomas Bayes, right? He was an English clergyman and also a mathematician. And he came out with the concept of Bayes' rule, which we use in Bayesian statistics. So Bayesian statistics is all based on Bayes' rule. And Bayes' rule is based on conditional probabilities. So Thomas Bayes came up with the Bayes' rule, which says that the probability of event B, given that event A has also occurred, is a function of the probability of event A given event B multiplied by the probability of event B divided by the probability of event A. So, for example, we have established that hunger and not eating are joint events. So if we want to find the probability of you experiencing hunger, it is giving us the probability of you not eating multiplied by the probability of you going hungry divided by the probability of you not eating. And that is what is called conditional probabilities. So all the Bayesian statistics we are going to learn is based on this particular formula we have here. It's simple. So Bayesian statistics is all about conditional probabilities. The probability of event B given A. So this is the probability of event B given A. Like I've established, this line here means probability of event B given event A. That is how it is read in statistics. This one here is the probability of event A given event B. Then the probability of event B is called the marginal probability of event B. So this here is called marginal probability or independent probability. And this one is also another marginal probability of event A. So focus on this formula because that is what we are going to use. So I'll explain further when it comes to this conditional probability. Any questions so far?
Cuando te refieres a marginal, ¿viene siendo mi evento condicional?
Yeah, so marginal probability is just the name that we give it to it. The whole formula there is the conditional probability. So the marginal probability is only this one and this one. But the whole formula is what is called conditional probability, right? So this one, probability of A, probability of B are called marginal probability or independent probability. But when you look at this whole formula, conditional probability. See?
Entonces, allí la probabilidad de que haya sucedido B, dado que ya sucedió el evento A, es el que está allí empezando la fórmula, ¿es así? Thank you.
So the formula you are seeing is the probability that event B has occurred given A, and it is a function of all those probabilities there. So because the two events are joint events, we evaluate them with conditional probabilities. They go hand in hand, right? So then what is Bayesian statistics, right? So Bayesian statistics is a mathematical procedure that applies probabilities to statistical problem. So Bayesian applies probability to any statistical problem. Now, the probability in Bayesian one of them expresses a degree of belief in the event. The probability expresses a degree of belief in the event. And the degree of belief of that event occurring is based on prior knowledge about that event, such as the results of a previous experiment or a personal belief about the event. And Bayesian statistics use Bayes' theorem to compute and update probabilities about obtaining a new data. I will explain further. So Bayesian statistics is based on prior knowledge about something. Okay. So Bayesian statistics is that when we are evaluating Bayesian statistics or Bayesian probability, we have an event or an experiment, but we have a prior knowledge about that event. So we incorporate that prior knowledge that we have concerning that event into our current event, and that is Bayesian statistics. So for example, my home country, Ghana, I like football, right? My home country, Ghana and Brazil, they've played football games 4 times. And anytime Ghana meets Brazil, Brazil scores us, right? So assuming Brazil is coming to play Ghana again now, which team will you support? Will you support Ghana or will you support Brazil? Who do you think is likely to win? Brazil. And the reason why you are saying Brazil is because previously they've encountered each other before. So we have some knowledge. And so because they are coming to play now, we are updating our current event based on what we already know about what happened in the past. And that is Bayesian statistics. See? So some of the decisions you may have made in life is based on Bayesian statistics. You didn't think of it as being Bayesian, but in actual fact, you were doing Bayesian statistics. So another example. Okay, let me use schools. Assuming there is a good school, right? Anytime they write exams like college or high school, all the students do very well. They go to the Ivy League schools, the big schools, right? If you were a parent, would you rather send your child to that school or you send your child to a different school? Obviously, you send your child to that good school. Why? Because previously, when they write the exams, all the students do very well. And so if you're a parent, you want to send your child to that school instead of sending your child to another school. And that is Bayesian statistics. So the prior knowledge we have about the event is what we incorporate into the current event that we want to look at. And that is Bayesian for you. So you see, initially when I started, I told you guys that some of the decisions we make in life is based on Bayesian statistics, but we don't usually think of it in that way. So Bayesian statistics is around us in our everyday life, and we use them all the time without knowing. Okay, so any questions? I hope I've been able to convince you to use Bayesian statistics. All right? Okay. Any questions? So who can give us an example of some decision that they took which was based on Bayesian statistics? Now that we all know what Bayesian statistics is. Anybody? I'm sure everyone has done something that their current decision was based on past experience.
One of the example, it could be, why did you come to this workshop? Have you heard about WorldPop before? How many people heard about WorldPop before coming to this workshop? Okay, 4. So for the rest of you, is it your first time that you hear about WorldPop? Okay. So for those who came to this workshop, that would be an example. You have heard about WorldPop, Probably you have attended a previous session like training, then you realize this is good. Then based on that, you made a Bayesian decision to come to this workshop.
All right, yes.
Okay.
So as my colleague was saying, even if you've not heard of WorldPop before, we assign what is called zero probability, right? So you are only evaluating the situation at the moment, and that is still Bayesian statistics. So in Bayesian statistics, when you have a strong knowledge about something like Ghana, Brazil scoring Ghana, we give it more weight. And when you don't have any knowledge, you give it maybe zero probability because we don't know, and that is still Bayesian. So it's still Bayesian, the fact that you've not heard of WorldPop before. So every decision you take in this life is either Bayesian. So to me, I'm very biased. I wish colleges would teach more Bayesian and than frequentist statistics, except that it's very challenging when it comes to computation. So most people move away from it, right? So we can still move on. Okay, so this is an example, but I have given you more examples with respect to football. So assuming someone told you there's a very good restaurant and he said, oh, we can rate that restaurant as a 5-star restaurant, right? Then you go to the restaurant and you eat their noodles and you realize their noodles is not good, right? So based on that, you update your current information and you rate that restaurant to be a 3-star restaurant, because even though your friend told you it was 5-star, you went there, you had some noodles, it wasn't good. So now you are rating it 3-star. Then the next time you go there again, and then you eat their tasty Alfredo. I don't know what meal is this, and you realize, oh, the Alfredo is now good. So now you rate it 4-star, right? You give it 4-star because the Alfredo is good. So you are changing your decisions based on past events, right? So you pick past events, bring it into the current event, then the current event, you also change it as you go along, right? So that is what we do in Bayesian. Knowledge is very powerful. So we are back to the Bayes rule again, right? And this time around, we decompose the Bayes rule into, I'll explain this in the next slide. But when we apply conditional probabilities to Bayesian statistics, the probability of a parameter given data is given as the probability of a data given the parameter multiplied by the probability of the parameters divided by the probability of data, right? So this thing here is the same thing here. The only thing changing is the names, right? I'll explain parameters for you in the next slide. But data is when you have any data set. So when you have any data set and you want to estimate some parameters from that data, like the regression we did, then we evaluate it based on Bayes rules or conditional probability. So then, what is a parameter? In statistics, a parameter is any unobserved quantity that we need to estimate. Any unobserved quantity that we need to estimate is a parameter. So yesterday, when we wrote our regression formula, if you do remember, we had our response, also known as the dependent variable, being equal to an intercept, right? A baseline model plus our coefficient multiplied by our covariate plus some kind of random error or noise which we cannot account for, or we don't know why that error is happening, right? So that becomes our regression equation. Do we all remember the regression equation? Right? So when you do any regression, this is how your regression equation looks like. So you have the outcome you are interested in being your dependent variable. Then we have an intercept. Then we have our coefficient here. Then we have an error. We can further write the response in statistics. The response can be written as y, right? Equals the intercept plus the coefficient of the covariate. Now, this time around, replacing our covariate with xp here, plus our error. We can, now the intercept in statistics is called an alpha here, right? The intercept, which is the baseline model. The intercept simply means that if you don't have any independent variable in your regression, what is the mean estimate that you will get? That is the intercept. The intercept is called an alpha. Then the coefficient that you get is called a beta value. Then the error is called a sigma. Now, these values, when we do regression, we don't know them. So we need to estimate them in our regression model. And those things, these alpha, beta, sigma, or your intercept, your coefficient, or an error are the parameters that we need to estimate. So those names you see there are what is called parameters in statistics. So the whole idea of estimating, doing a regression analysis is to estimate those parameters. What is our intercept value? What is our coefficient? And what is our error, right? So those values, when we add them together, we are able to predict our outcome variable, which is y1. See? Are we okay? Is it confusing? A bit. So yesterday when we did the linear regression, right? We saw our coefficient like crime, number of bedrooms, right? So those coefficients that we had from our regression are the beta values. They are called the beta values. And we also saw our intercept, right? We saw the residuals, which is the error value, right? So those are parameters. I mean, I know it can be very hard to understand some of these things as we learn right now, but just read around them, because this is what we use in our population modeling, right? So even though it may be hard to grasp now, when you go home, just try and read around them. So they are called parameters. Alpha, beta, sigma are the parameters that we estimate in our regression model. So in Bayesian statistics, the probability of getting a parameter, given that you have a data, is equal to the probability of a data given the parameter multiplied by the probability of the parameters divided by the probability of the data. And we say the parameters are alpha, beta, sigma. they are unobserved quantities. We don't know them. So we need to estimate them in our regression equation, right? So to estimate them in our regression equation, we use Bayes' rule to do the calculation. And this is all about Bayesian statistics. The probability of the parameter given the data is called posterior distribution. Posterior. So the probability of the parameter given the data is called the posterior distribution. Then the probability of the data given the parameter is called the likelihood function. So the likelihood function is a joint probability between the probability of the data given the parameters. Then the probability of the parameter is called the prior distribution. So you know I told you guys about prior knowledge. In doing Bayesian statistics, this is where we incorporate our prior knowledge. What do you know about the event? It could be that you have past knowledge or you don't have any knowledge at all. That is prior probability, right? So you see we've incorporated it into the model. Then we have the last one being the probability of the data, which is the marginal distribution of the data. So in Bayesian statistics, one of the characteristics that distinguishes Bayesian from frequentist statistics, what we learned yesterday, is this prior knowledge about an event. This is what distinguishes Bayesian statistics from frequentist statistics. So Bayesian is all about priors. Bayesian is all about priors. If we eliminate the prior from our model, then the results that we get is equivalent to the regression analysis that we did yesterday. So if you give it 0 probability, right, you are essentially doing a frequentist statistic because you get a similar result like doing a frequentist model. So always when someone asks you, oh, do you know about Bayesian? Tell them yes. And they ask you, okay, so what do you know? You said Bayesian, we incorporate priors into our model to account for past events, to update our current knowledge. So that is Bayesian. So we have posterior distribution, we have the likelihood function, we have our priors, and then we have our marginal distribution over here. Okay, so this is another way of writing it. So our posterior on the left side, we have our likelihood multiplied by our prior divided by our marginal distribution. And here is the same prior belief. Then we update our posterior so that we can get new evidence with respect to whatever we are looking at. Any questions so far? Okay, so when we have any data set and we need to estimate some parameters like a regression, we have to do the computation, right? The calculation. And how that is done is through previously, is through simulating from the priors to get some values from the simulation. So we do a simulation study, and then we draw from that particular simulation study. But it's not simple. The calculation can be computationally very challenging, right? So we have ways of going around it or doing it. One of the things that happens with Bayes' theorem, or in terms of evaluating a given parameter, is the fact that the marginal distribution at the base here is very challenging to calculate, right? It's very sophisticated to calculate. And so in terms of the Bayesian model, they always drop this marginal distribution. We don't include it in our model, right? So then the Bayesian model only becomes the posterior equals the likelihood times the prior. This marginal distribution, which is the base, is always dropped from the calculation because it can be very challenging to do the calculation when you have that marginal distribution, which is the probability of you evaluating the data. It's very hard to do that, so we drop it. So here, we drop the marginal distribution. So voila, we have a new Bayesian formula. So to get the posterior of any parameter, this sign here is called proportion. So the posterior of any parameter you are interested in is proportional to the likelihood multiplied by the prior, and you get your results. Okay. And in doing the computation, we have an algorithm or a mathematical method called Markov chain Monte Carlo simulation. Markov chain Monte Carlo simulation is one of the algorithms that we use to evaluate our parameter of interest. And Monte Carlo is a mathematical method for drawing samples from a distribution in order to obtain parameter estimates. And Markov chain is a sequence of correlated samples in which a future value only depends on the present given the past, right? So we use Markov chain to estimate our posterior distribution by simulating and then drawing samples from it. And that is Markov chain Monte Carlo. So the stand that we installed is what is simulating our posterior and then drawing samples for us to see if our chains are converging at a particular value, right? So that is one of the ways we do the computation in Bayesian statistics. Recently, there has been some development. So we have another algorithm called INLA. The full meaning of INLA is integrated nested Laplace approximation. You can Google it. So with INLA, it's a bit easy when you are making the computation. It's more straightforward compared to the Markov chain Monte Carlo simulation method. So if you are interested in that, you can also have a look at that particular algorithm. Okay, so I think this is the kind of the last slide. Any question so far? Any questions so far? So we've established that in making Bayesian statistics, we rely on prior knowledge about the event, then updates our current knowledge. Here in this slide, I just want to give some few differences between Bayesian statistics and frequentist model. You don't need to really understand the whole thing, but just some differences between them. And one of the differences between the frequentist statistics, so when I say frequentist statistics, the statistics that we did yesterday is a frequentist statistics. One of the difference between frequentist statistics and Bayesian statistics has to do with the way we interpret probability, right? So in frequentist statistics, we often use the p-value to either reject the null hypothesis or we fail to reject the null hypothesis. And the p-value, we can't make a true probability statement regarding a p-value in frequentist statistics. The p-value is actually a statement regarding the null hypothesis. So we can't make a true probability statement regarding the null hypothesis, but rather the p-value is a statement concerning the probability of making a type 1 error, the probability of rejecting the null when in fact it's true, right? So this is a bit theoretical. I don't expect you to grasp the theory behind it, but we don't make probability statements regarding the p-values that we get in frequentist statistics. But it's actually a probability statement concerning the null hypothesis that you are evaluating in your model. But because Bayesian statistics is all about probability, we can easily make a probability statement regarding a parameter of interest. So if, let's say, you are evaluating population density, for example, we can make a probability statement that the probability that Panama City has a very high population density is 90%. So we can make that statement when we use Bayesian statistics, but we can't make similar statements when we are using frequentist statistics. The second thing that we also need to know is that in frequentist models, the parameters that we estimate, they are always constant value, right? They are always constant value or phase constant. But in Bayesian statistics, the parameters that we are interested in are random value. And this is what it means. In frequentist statistics, when you estimate your coefficient, you get a single value. It can be 2.5, it can be 1. But in Bayesian, what you get is a distribution of your coefficient. So your coefficient, it gives a number of values, right? So it becomes a distribution. It's not a single value. So what we mostly do in Bayesian statistics is that when you get your distribution of that parameter that you are evaluating, you can either use some measures of central tendency, which could either be the mean or the median value, to evaluate all those posterior distribution that you have estimated in your model. So whilst the frequentist will give you a straightforward answer, it will give you one number, in Bayesian, it is actually a probability distribution. And then we summarize that distribution with the mean or a median. The accepted norm generally is using the mean, but some people tend to use the median. So the posterior that you get from doing a Bayesian analysis is a large number, which is a distribution and not a single value. You summarize it and you get the mean value. And the mean value that you get, assuming in Bayesian you've done your analysis and you are getting numbers from 1, 2, 3, 4 until 10, when you summarize it, you get a mean value when you compare that mean value with a frequentist statistics, they are almost always close, especially if you use non-informative knowledge or you assign 0 prior to your modeling, then the information, the two statistics will be quite the same. And in terms of frequentist statistics, when we are making inference, is based on only the likelihood of observing a given parameter, given the data. But in Bayesian, it involves the likelihood and it also involves your prior knowledge. So frequentist is only the likelihood. In Bayesian, our prior knowledge and then our likelihood combined. So the last one is that frequentist statistics doesn't use prior. We don't use any prior in frequentist statistics, but in Bayesian statistics, we use priors to evaluate our model. So these are some few differences that we have when it comes to either Bayesian or a frequentist model. Natalia, make it big for me. I don't know what happened. Yes, so if you want to read more, this was just an introduction, but if you are interested in learning more on Bayesian statistics, there are some resources that you can read. So I think the links are there. You can go ahead and read about them. Any questions so far? So now we are all Bayesian experts, right? Yeah. So see, yeah, that's good. Let me jump back quickly and let me talk briefly about how we assign priors to the parameters. So this is the formula for a regression model, right? Our alpha, our beta, and our sigma. And we have already established that these are called parameters, alpha, beta, sigma. So in Bayesian analysis, in Bayesian regression, we assign priors to each of them. So alpha will have its own prior, right? Beta here will have its own prior. What is your level of knowledge of the expected value of beta? You incorporate it here. Our sigma will have its own prior. So all the parameters in the model are assigned priors in terms of the regression modeling. So yeah, that is it. So we are going to apply this to estimate our population. All right. Any question? I think we have about 30 minutes before the break, right? Okay, sure.
Thank you. No, just the thing is that en español. Okay. Gracias. Solamente una precisión, y es que los parámetros de interés no es que sean aleatorios, sino es más bien la incertidumbre del investigador acerca de la localización del parámetro, lo que tendría una distribución de probabilidad en el contexto bayesiano, pero al final siguen siendo cantidades desconocidas y fijas. Pero la probabilidad o la distribución de probabilidad previa o a priori está más dada por esta incertidumbre del investigador sobre dónde estaría ese parámetro. Gracias.
Okay, thank you so much for making that comment. Yeah. So yeah, as he was saying, the posterior that you get, gives the uncertainty regards to the parameter of interest, right? So he's right in making that comment. So one good thing about Bayesian is that you are always able to estimate an uncertainty regarding parameter of interest. So if you say the population density of Panama City is 4, what is our level of uncertainty? And our level of uncertainty can go below, let's say, population density being like 2.5 all the way to 5. So we have that uncertainty regarding our population density for Panama City. And that is one of the powerful things about Bayesian statistics. You are always able to estimate the uncertainty regarding a particular parameter. Good. All right. Can we go ahead or take a break? Okay, so we are going to do our first Bayesian model in R. So open to your day 3 folder. Open to your day 3 folder. The script, go back. Go to my documents. Okay, when you open to your day 3 folder, scroll down, open workflow 1, workflow1.r. Have you all opened workflow 1? So we are coming to do a simple Bayesian regression. A simple Bayesian regression. We have all opened it, right? Okay. So these are the packages that we are going to use. So you already have your tidyverse. I don't think you have ggdark. So install this ggdark package. Install cable extra package. You already have rstan, so you don't need to install it. We already have core plot. We used it yesterday for the correlation. Then you install your base plot package. So we all know how to install packages. So any package that you are missing, try and install it on your own. Natalia, can you scroll back this?
So this one will make the underscore.
Yeah. Yes.
But no, I haven't done it.
No, that one it's part of the it's there. They don't need to install anything. So yeah.
This one will need to make it.
So when you get here, this is actually a function that we created. So it's not a package. So just run this one and it will run. So don't worry about this one and this one. but any package you are missing, especially base plot, whatever package, try and install them. Yes, and also change your drive path, only change this one. You know, yesterday we changed the path, right? So just copy the same path here and replace it. Where your working directory is located, make sure you change it, otherwise your script will not work. Let me know if you need any help.
Una cosa, asegúrense que en donde dice el drive path, de que tenga el día 3, ¿ok? También, porque si ponen solo el path al workshop, no les va a llegar al data ni al script, ¿ok?
Natalia,
Dime, Okay. Por favor, asegúrense que cierran los trabajos que hicimos ayer. Si los tienen, por ejemplo, en alguna ventana, ciérrenlos y una vez corran esa línea número 10, se va a borrar todo lo que tengan